Okay, here we are continuing with line integrals and vector fields. And I'm not going to kid you, this is probably one of the toughest sections from this chapter. So pay close attention, especially to the end when we do a construction that I will ask you to do tomorrow in the workshop. So let's jump right into this. Recall from 16.1, we had looked at a function. It was something like f of x, y, z equals x minus 3y plus c. And we looked at integrating it over this curve, c1. And when we did that, we got 0. And then we looked at combining two curves, c2 and c3. And we looked at the sum of these, and it wasn't equal to 0. And so what I said then was, and what we established with this is that note, I want black here, the path you take from point A to point B along C changes the integral value. And the question people had was, well, what if they were equal? In fact, what if any path gave you the same integral value? So it doesn't matter what it was, whether you took 5 steps or 2 steps or 1 step to get from point A to point B. What if all those gave you the same value? And this is called path independence. So definition, let cap F be a vector field suppose that for any 2 points, A and B, in some region D of this field, the line integral equals some constant for any path from A to B. Then f dot dr over C is path independent, and cap F is a conservative vector field. Okay, and this comes from physics. It's the principle of conservation of energy, meaning it's like gravity, right? If you're out in space and you go vertically, sideways, horizontally, downwards in circles, you do the same amount of work. Okay. And so, okay, there's a bunch of definitions and theorems here that really help us along. So here's a definition. So let F be a vector field. And assume F is a gradient vector field for some F. Then F is a is a potential function for f. Okay, and then something very cool here. This big theorem. It's the fundamental theorem of line integrals. Fundamental theorem of line integrals. Okay. And it's a big one. And if you know how to use this, it will make your life incredibly easier in the weeks to come. Okay. Come back, pen. So here we go. Let's see. Be a smooth curve from point A to point B, where C is parametrized by some r sub t with t running from A to B. Let f be a differentiable function with gradient vector field f equaling del f. So now we've made the conservative vector field from a function. Then the conclusion is the integral around the curve is f of b minus f of a. This looks so much like the fundamental theorem of calculus that that's why it's called the fundamental theorem of line integrals, right? Make this prettier here. And so, as long as you know what f is, and as long as cap f is the gradient of f, then your integrations are very, very simple. All you do is look at the endpoints and evaluate it at f. Okay. All right. So, theorem number 2. So let f be this field we've been working with. Then the field f is conservative if and only if f is a gradient field for some function f. In other words, del f equals f. And yes, f is a potential function for cap f. Okay. So there's two directions this theorem can go in. If you build f to be a field from a function, then it's automatically conservative. Or if f is conservative, there is a function out there that turned it into a gradient vector field. And that's the hard direction, and that's what today's really about. Finding this little f. Okay. All right, let's look at some examples here. Try and clarify these ideas. let's let f equal yzi plus xzj plus xyk. So let's compute the work done along a smooth curve C from -139 to 16 minus 4. Now, if you're just working in chapter 16.2, the one we just completed, what we need is a parametrization for C, because we want to go f of r. First we have to compute that, then we have to find dr dt and compute that, and then we have to go from C's parametric interval, and then do all that work like we did in the last homework. However, if f is conservative, and we find its potential function little f, then all we have to do is, by the ftli on the integral is equal to f of 16 minus 4 minus f of -139. Okay. Well, those are derivatives, right? And they all look sort of related. So I'm going to take a big old guess here. I'm going to guess that f of x, y, z is xyz. This is just an educated guess because, well, look, f sub x is yz, f sub y is xz, and x sub z is xy. So we have yz, xz, xy. Sure enough, our guess was right. And f is conservative. Not only that, we found little f, the potential function. So, by the fundamental theorem of line integrals, f dot dr is (1) 6 minus 4 minus -1 3 9, and that's 3. Right? Okay, and so, well, you know, math is not really a guessing game unless you get lucky, and this was contrived to be lucky. But we're going to see here in a second that if you, well, first we're going to have a test to show if f is conservative, and then we're going to have a technique to find out if, in fact, we can find little f. So let's do that. There's another theorem. Let f be mi plus nj plus pk. Oops. Then f is conservative if and only if py equals nz, mz equals px, and nx equals my. Now those of you who took DFEQs with me will remember this. This has to do with exact equations, and if you read the book you'll see that we are in fact working with exact equations here. Alright, so that should be mz equals px, not 9x. Okay. So example, I think this is example 2. Show that f equals 2x minus 3i minus zj plus cosine zk is not conservative. So up here, number 1 says, what's py? Py is 0. nz is minus 9 sine z. Not, I looked at the wrong one here. Hold on. nz is minus 1. Py is not equal to nz, so not conservative. Okay. Example 3. Now pay attention. Okay, here's my field. E to the x cosine y plus yz I plus xz minus e to the x sine y j plus xy plus z k. Let me make sure I wrote this down right. E to the x cosine y plus yz. Xz minus e to the x sine y j. Xy plus z. Okay, so first of all, is it conservative? Py equals x and z equals x. Check. 2 mz and px. mz equals y. Px equals y. Check. And 3 nx equals z and my equals Sorry, I had a brain moment there. Let me do this again. Nx, I'm looking at two examples at once. Okay. Nx is z minus e to the x sine y. Okay. And now my equals z minus e to the x sine y. Check. Okay. Whew. On this sheet, I have 3 examples, and I keep looking at the wrong one and writing down the wrong thing. So there we go. I should have just done the problem straight by itself, right off the computer. So this tells me that f is conservative. Now we need to find Nemo, or f. Potential function for cap f. Now this is really hard. Okay. And if you had me for diffy q's, we did this. So, and Reed and I argued a lot about how to do this. But here we go. So A, set f sub x equal to m, right? Because that's what this means. If we had cap f already, to find del f, we take the x partial. Now m is, what's m? It's e to the x cosine y plus yz, right? So we set f of x equal to m, which is e to the x cosine y. So we want f. So we're going to integrate both sides of this equation. Oops. With respect to x. Come on, red. That's going to be really big. There we go. Okay. With respect to x here. Because we want f of x to become x. So we integrate to make the x's come up. And that's an equal sign. Well, on the left-hand side, you use the fundamental theorem of calculus, and you get f. And on the right-hand side, you integrate with respect to x. Your first term, you just get e to the x cosine y, because the integral of e to the x is e to the x, and cosine y is a constant. And then over here in the second term, you pick up an x, so it's going to be yz x. And now for the part that's a little tougher to swallow. Generally, your constant of integration is an actual constant. But because we're working with partials here, you actually pick up a function of y and z. Now you need to let that marinate for a second. Right? If I wanted to take this problem and go this way with it, if I wanted to take the x partial with respect to this function here, what would I get? I get e to the x cosine y, yz, and then any function over here that had a y or a z only in it with no x's, that derivative would be 0. So I'd get my integrand back again. All right? I'm going to say that again. I integrated this partial with respect to x to get f. And I picked up this g to the yz, g of y of z on the right here. If I was going backwards and taking the x partial, this guy would be e to the x cosine y. This would be yz. And then any function that was only in terms of y or z or both would have a derivative of 0. Okay. So now I have my f. F of x, y, z is e to the x cosine y plus x, y, z plus function g of y of z. And we've satisfied the first condition for conservativeness, that fx equals m. Okay, b. we want f sub y. So we want f sub y, and we're going to set that equal to n, because that's what we're supposed to do. All right, well, we know what f is, so we want f of y. So now take the y partial of this guy. Okay. So f of y is minus e to the x sine y plus xc plus the partial with respect to y of this function g, which we don't know, right? It's an unknown function. Here's the kicker, but fy equals n. Okay, and so what we have is that this line above here, this minus e to the x sine y plus xy, see, equals n. And what's n? N is this guy, e to the z, sorry, x to the z minus e to the x sine y. Make sure I get that right. X to the z minus e to the x sine y. So, okay, this guy equals this, and this equals that. So this says the partial with respect to y of yz has no y's in it. So it must be a function of z only, or just an old constant. Right? Because if there was a y in there, it would match up with n, and there isn't. So it must be that there's only z's in there, or just constants. Okay. So now I'm going to rewrite. My f, my little f here. So little f is e to the x cosine y plus xyz plus g of z. And you see how this changed? So that step told us that there's no y in this extra function. Okay. Part 3, or C, I should say, if I'm lettering here. Now we compute f of z, which is going to equal to p, right? So what's f of z? F of z is, the first term gives me 0, the second term gives me xy, and this third term gives me a g prime of z. And what's p? I need to find p again. P is, where the hell are you, p? xy plus z. Okay, so this says that g prime of z equals z, which says g of z is c squared over 2 plus a constant. So now we put the whole thing together here. I guess I'm going to stick with blue. And so my potential function f of x, y, z is e to the x cosine y plus xyz plus c squared over 2 plus k. Whew. Okay, now let's check this, right? That's always fun. Because del f is supposed to equal cap f. Alright, let's do this. Right? Let's compute del f. So m is going to be e to the x cosine y plus yz I plus f sub y is minus e to the x sine y minus e to the x sine y What am I integrating with respect to, or differentiating with respect to y? Plus x z j. And in the third one, it's z, so it's xy plus z k. Let's check. Do these match? E to the x cosine y plus yz. Yes. xc minus e to the x sine y. Yes. And I missed it. xy plus c, yes. Check. Okay. So here's homework 13. This is all of it. Five, 6, 9, and 10. 24. 24, 25, 30, and 32. Now, if you show up tomorrow for this workshop, and you haven't done at least these 4, you're going to get destroyed. So you have to do at least 5, 6, and 9 tonight, and preferably all 4 of them. If you had to go with 24, that would be great. But really, you want to do 5, 6, 9, and 10. And if that's not enough motivation for you for guided practice, do this right now, and then we'll talk. Tell me, is f conservative? If so, find little f.